Good morning, everyone. Thank you for attending to this Innovating Organic Chemistry uh, webinar workshop that we are organizing under the Photo2Fuel project. My name is Alejandro Gonzalez. I'm senior researcher of IDENER, and together with CINEA, our communication and dissemination partner in the Photo2Fuel project, um, we are we have the pleasure to be hosting this workshop, in which we are going to take the opportunity to be in such a fundamental, instrumental, and enriching place like it's the Van Hoff Institute for Molecular Science in the University of Amsterdam. I say that we wanted to take this opportunity, given that Van Hoff was the first Nobel Prize of Chemistry in 1901. We didn't think about any better opportunity to host this type of workshop in innovating organic chemistry and how it's helping us and helping humanity in exploring technologies and sustainable solutions. So as I say, we had the opportunity that under Photo2Fuel, which is a European funded project, basically using organic chemistry and multidisciplinary approach to develop a carbon utilization technology. It was a really nice opportunity to explore other researchers and novel solutions that are being put in place to help us becoming a decarbonized continent in Europe. So just talking a little bit more about the Photo2Fuel project. We are 8 partners from 5 different countries, in which IDENER is coordinating the project. And as I say, it's a multidisciplinary team for the development of a carbon utilization technology. It started a couple of years ago on the 1st of September 2022. We are approaching our last 6 months for the conclusion of the project. I just wanted to make a really overview of the actual technology itself. As I said, it's a carbon utilization technology that is using the capability of some microorganisms strains to process CO2 by their natural metabolism to convert it in valuable chemicals or even biofuels. The piece of innovation that we are trying to apply in Photo2Fuel is given the capability to these microorganisms that naturally cannot use or cannot harness the energy from light source by adding photosensitizers to their membranes. This will make them take the advantage of using that sunlight to gather energy for the metabolism enhancement and the production of these valuable chemicals that I'm mentioning. To further our scaling this technology, the plan is to become an autosufficient mini solar plant with 100% solar irradiance as this energy source. And also we are working in some of our main tasks in the product separation of the main outputs of the process. I just wanted to also make a really brief overview on the agenda that we are going today, in which we have 6 different speakers that they will talk specifically about their piece of research being carried out here in the Van Hoff Institute of Molecular Science. So there are going to be really brief talks of a total of 15 minutes, in which we are going to have just 5 minutes for questions and answers in case they arise. I'll be introducing one by one each of the following speakers, but I wanted to take the opportunity to start with Miguel Claros Casillas, which is our researcher in the NOAL's research group. And actually participating actively in Work Package 4 and the upscaling of the Photo2Fuel technology. So Miguel research focused on the development and study of innovative reactors for both batch and flow systems, specifically designed for photochemical and photothermal reactions. By emphasizing the fundamental understanding of reaction components and their interactions, his work aims to enable organic transformations while integrating automation for reaction development and mechanistic studies. And Miguel will present in the coming minutes the work done by the University of Amsterdam on developing a photochemical reactor for the upscaling of the CO2 conversion into useful fuels and chemicals. So thank you very much, Miguel. The floor is yours. We are really looking forward to hear you.
Thanks for the opportunity to give me the opportunity to show my work here related with the Photo2Fuel. So I'm Miguel Claros, postdoctoral researcher in Northwest Research Group. We are quite a broad group that has different research lines. Basically, a gas team that relates the use of flow techniques in the gas-liquid reactions, but also an automation team that is focused in the use of new technologies to be able to use more efficiently organic chemistry, and then photochemistry. Some team is electrochemistry. That all of them you are going to see today. But I will center my attention more in the LSEPM team. That is mainly there's a bit delay. It's mainly made with different researchers that we work together, generally engineers, organic chemists, organometallic chemists. So I will briefly explain you the concept of the Photo2Fuel. Is to use bacteria that are also working together with photocatalysts. And our role here is to develop a mini solar plant that can handle these microorganisms to produce fuels from CO2. So this is basically the concept of the project. So some bacteria with colloidal dials that will be mixed into a reactor to produce methane or acetic acid. So when we look more in detail into the system, we can see different challenges. As for example, the temperature that these organisms require, the time of the reaction that they need, and also the risk of the growing of the bacteria can generate a clogging of the reactor. That is a challenge in flow chemistry. This is I lost the connection, I think. But it lost the connection. Cool. So in the part of the colloidal dials, we don't have at the beginning very lot of challenges. So this is a summary of the reactor. It's based on the CO2 cylinder. It's gonna be controlled with the pressure control, and then it's gonna be pumped to the reaction. And then thanks of the peristaltic pump, it can be delivered to the reactor that is based on a PMMA reactor. It's a polymer that can let the light to pass through. All the light and the temperature of the reactor is going to be controlled in our custom solar simulator. And then it's going to pump through a flow NMR that can be measured the generation of our product, and then pumping in again to the reservoir where the bacteria is going to be there under control conditions. This is how the reactor at the low scale looks like in reality, with a reservoir, back pressure regulator to control the pressure of the system, an electronic box that can automate all the pumping and not in this case the pressure, but also the light. A peristaltic pump that will allow us to pump the solution into the reactor and back to the reservoir, and the LSEPM reactor that in this case is coated with a blue light, but this can be module depending on the organic dye we are going to use. So So everything, as I said, can be automated with the presence of automated pressure controls. The temperature of the reservoir can be also automated, also the flow rate of the pump, the light, the temperature, and all the results can be recorded with the flow NMR, and then we can make the system automated. In this slide, I'm showing a bit of a summary of the automation system with the mass flow controller that will control the flow of the different gases, CO2, hydrogen, but also it's possible to change the gases to nitrogen or to control the atmosphere we want. Also, the light can be controlled, the intensity of the light with Arduino chips, the temperature of the reactor with a PAT controller, and also the pressure of the whole system with a back pressure regulator. This setup has been proved to work in a previous work from our group that we developed a photo-assisted production of CO or methane from CO2, and we could control the conditions to generate CO in a demand manner to be able to generate carbon-negative products in a quite specific manner. So this is more or less the setup that we developed for this project, and this is how it looks like in reality. This is the reservoir with the inlet from the reactor and the outlet that is going to be pumped to the reactor, and also the inlet of the CO2 that can be controlled by the pressure and the amount of CO2 needed in the reaction. Then this is an image of the peristaltic pump that we deliver the liquid into the reactor and pumping back to the reservoir, and also the back pressure regulator that will control the pressure of our system. So this is a general picture where we can see all the things. And in this slide, we can see how it looks like the scale up version when it's in the sun. But unluckily, in the Netherlands, we don't have too much, so we can just select some days to put our reactor in the garden and to try to do the reaction there. Everything, as I said, is automated with this green box. And this was a bit the summary of our part in the consortium. Thank you very much for all your attention, and I'm here to answer all the questions needed.
Thank you very much, Miguel, for such a nice presentation. Indeed, it's a really nice setup that we have just we have managed to achieve under the Photo2Fuel project, which is developing these first stages of a bioreactor in which the catalysis of the Photo2Fuel reaction will happen. It seems very promising. We are under the testing parts and progress of the project, and stay tuned for our website and social networks to see how everything performs. I just wanted to take the opportunity to check if there are any questions from the audience. I don't know if here we are, as I said, we are hosting this workshop in the Bankhof Institute. We have some people present in the actual room. I don't know if there are any questions that anybody wants to do. If not, maybe we can go straight to this next presentations. Dimitri Nargoni, also PhD candidate under the Noel's research group. And Dimitri specializes in flow photochemistry involving gaseous reagents, exploring innovative methods to advance this emerging field. During the workshop, Dimitri will cover flow photochemistry with gaseous reagents, starting from the basic principles and highlighting the 6 papers that came from Noel's group on this matter. So welcome, Dimitri. Thank you very much for your presentation. The floor is yours.
Right. Let's see how big of a delay is. Okay. So again, hello everyone. My name is Dmitry Nagorny, and today I'm going to highlight the works that have been going on in the NEL research group for the last few years on the topic of photocatalytic functionalization of gaseous alkanes in flow. But first, I think it's very important to ask, to start with, why are we doing this? So we extract natural gases from Earth on enormous scales every year, which is mainly made of natural gas mainly made of methane with impurities of ethane and other gases. However, the main use of these chemicals are fuels because they burn cleaner and leave less traces compared to other fuels as coal and so on. But if you want to use those bulk chemicals to synthesize complex molecules, you really require challenging activation steps. For example, if you want to halogenate methane, for example, you need to react it with chlorine gas or bromine gas at high temperatures and elevated pressures, or use light activations. And those processes are inherently inefficient. They are low yielding and have low selectivity for the desired product. So we asked ourselves, how can we use those abundant materials like methane and ethane to make complex value-added products like pharmaceuticals, materials, and agrochemicals in an efficient way and an atom economical way? And we achieved the conclusion that we require a new approach, and that is the photochemical functionalization of those gases alkanes in flow. So now I'll go through the basic concepts behind our works. So firstly, when you want to react to chemicals, you have to bring them in contact. And that is particularly difficult when one of the reagents is a liquid and another one is a gas, because they want to separate from each other. The gas wants to go to the gaseous phase, liquid stays a liquid. Most gaseous reagents have low solubilities in organic solvents. And that's why we have to use increased pressures to force those gases into the liquid phase. And this is a normal, usual batch setup that we use in the lab, a high pressure reactor, also called a PAR reactor. But obviously it possesses some drawbacks. And for me, the most obvious one is the safety concern. So if something goes wrong and you overshoot the pressure, you don't want to be in a way of a 5 or 10 kilo projectile, a stainless steel projectile. Additionally, if you think about scaling up this setup to, let's say, a 10-liter reactor or a 50-liter reactor or a 1,000-liter reactor, a lot of safety concerns emerge from those. Also, it is very difficult to dose precisely your reagent. Usually, you just fill the whole reactor with gas. You don't really have control over how much of gas you put in, like 30, 50, or 100 equivalents, which is a huge excess. So all those drawbacks are mitigated or improved if you move to a flow setup that looks like something like the picture on the top right. So as the name suggests, a flow setup. In a flow setup, we flow our reaction mixtures through narrow tubes. It's a cheap and scalable alternative. So the tubes are made of plastic. We have kilometers of them, of those tubes downstairs in the lab. In principle, you can scale it up and as much as you want. But I think the main benefit of flow chemistry for gaseous reagents is the improved mixing. So by using a flow setup, you increase the contact area, the surface area between the gas and the liquid. So you have more mixing between the two phases. So you have a bigger chance of the reaction, of your desired reaction happening, of you activating the gas and reacting it. Additionally, if you want to increase the pressure in a flow reactor, all you have to do is use a back pressure regulator. As you can see the picture on the bottom right, which is just a small piece of plastic with a spring inside that can regulate the pressure in your whole system. And as it's nicely demonstrated here, the gas liquid mixtures, the gas liquid slugs are coming in from the right at a lower pressure and exit on the left at higher pressures. So you get better mixing because of higher surface areas, higher contact areas. You get improved safety because the worst thing that can happen, okay, the tube pops, okay, that's a bit of cleanup. But if the battery reactor pops, then you have a real trouble. So those are just some of the benefits of the flow chemistry in the for use of the gaseous reagents in flow. Additionally, it's very important to talk about the Beer-Lambert law, which states that the intensity of the light decays exponentially with the path length, which is nicely illustrated in the following two pictures. So if you have a flask, or in this case a cuvette, and you shine a light on it, it can only penetrate so far. And yeah, as you can see, the intensity decays exponentially, and you only barely scratch the surface of this whole flask. Alternatively, when you look at the picture on the right, on the flow setup, even with the same light source, you can penetrate the whole flow tube and deliver the required photons to your reaction mixture. So by having a good reactor design, you can really achieve a homogeneous irradiation of your reaction mixture, of your flow coil. You eliminate the dark zones, again with a good reactor setup, and yeah, overall you improve your irradiation, and you deliver the maximum amount of photons that are required to achieve your transformation. Moving on, I think it's very important to state that activating the bonds in the methane or ethane or other gaseous alkanes, it's extremely difficult. So it's a real thermodynamic challenge. The bond dissociation energy of those bonds is very high, much higher than the normal reagents that we use in organic synthesis. So for that, you really need a specialized catalyst. And we're lucky enough to have decatungstate, which is a cheap and easy to make polyoxometallate hydrogen atom transfer catalyst that can abstract hydrogen atoms from even the most difficult to abstract bonds like methane to form radicals that can be further functionalized, further used in other reactions. And yeah, as I said, it's cheap and easy to make, and all you have to do is excite it with light, near UV light at around 360 nanometers, and you got yourself a working catalyst. Also, you don't need a lot of it. You just need 1-2 mol% catalyst loading to achieve good reaction yields. So all these concepts came together in the first paper from our group, in which we combined light alkanes with olefins to obtain those CC coupled products, those drug-like molecules in a continuous flow setup at room temperature, mild conditions, with just 1 or 2 mol% of TBADT as a catalyst. And this was a really nice proof of concept that showed that we can indeed use light alkanes that are extremely difficult to functionalize for useful synthetic chemistry with synthetically useful yields as well. But we did not stop here. We decided to increase the complexity of the system and add another gas to fully make use of the benefits of using gases in flow chemistry. So here in the second paper from our group, we took the light alkanes, and with TBADT you could make the alkyl radicals, and this we trapped with CO, which is another gas, and then further functionalized it. So here again, all the benefits of flow chemistry for gases that I've mentioned before: better mixing, higher solubilities of gases at higher pressures come into play to achieve this transformation. Additionally, we also did the same reaction but using SO2 instead of CO. So again, you could functionalize light alkanes with SO2 to achieve those synthetically useful sulfones that are found in everyday pharmaceuticals and materials and so on. And finally, I think the most important paper in this line of research so far is the coupling of light alkanes with aryl or heteroaryl bromides in a nickel catalyzed cross-coupling reaction. I hope you all know that cross-coupling reactions are the bread and butter of organic chemistry and one of the most used reactions in chemistry, in industry overall. So the fact that we can use those light alkanes and couple them selectively with heteroaryl aryl bromides is a big achievement, I think. So, as a short conclusion, I hope I showed you, even briefly, that flow chemistry is safe, scalable, allows for better mixing, more precise reagent control, and improved irradiation. And I hope you also enjoyed the highlight of our works on the carbonylation, cross-coupling, and obviously there's definitely more to come. So thank you for your attention, and I'm happy to answer any questions.
Thank you so much, Dimitri, for such a nice presentation as well. I'm just really amazed about the pieces of researches and very innovative ones that you are bringing to the table. I'm amazed for that, and so I really thank you for this really, although brief, very enriching presentation on this workshop. I just have a very brief question in case anybody has any question and wanted to write it on the Q&A box. But I have just a very brief questions about, okay, is this technology that you're working on, what do you see the near future on the deployment for, I don't know, that scalable option? Is this something that can be, because it has a lot of potential to give solutions to the pharmacy sector, as you mentioned. So is it something that can in the near future be adopted at industrial scale, or is this still a long way to go to that part? Thank you.
Well, I'd love for it to be applied to industrial scales. I think we're still a bit off of that nice goal, but of course it is very important to functionalize those very, very abundant materials, the ones we have so much of. But I think adapting it to industrial scales requires a lot of engineering efforts, and even though we show this on a lab scale, on a small scale, bringing it to a plant, it requires much more work. But I think there is definitely potential. I hope and I believe.
Perfect. Thank you very much for your answer. I just wanted to link this with the actual I mean, the moment that we are hosting this workshop under the consortium meeting of Photo2Fuel, I just wanted to highlight the opportunity that Horizon Europe or any other European frameworks and fundings, you already know about this because you are main researchers are always looking for funding. And so, but this is, I just wanted to highlight that the opportunity that this type of frameworks gives to these emerging technologies to almost trying to scale up to industrial scale is something that we need to take into account, not miss. And it's actually that resembles a lot with what we are trying at Photo2Fuel. It's a very technology readiness, low technology readiness level innovation that we are exploring already some market penetration and some scalable options for that. So hopefully we will see this type of innovations coming up to market and trying the scalability very soon. That will be very good news. So thank you again, Dimitri, for your presentation. We wanted to present a video that we have prepared under the Photo2Fuel project that I wanted to share over this workshop. So I just will need to wait for our organizer.
Okay.
Since 1990, the European Union has made significant progress in reducing greenhouse gas emissions, achieving a remarkable 32.5% reduction by 2022. But the journey towards a sustainable future is far from over. By 2050, the European Union has set an ambitious goal to become the first climate-neutral continent. To achieve this, up to 477 million tons of CO2 must be captured and used effectively. This is where carbon capture, utilization or reuse plays a crucial role. CCU is a set of technological solutions that involves capturing carbon dioxide emissions from sources like industrial plants and power stations, and then converting the captured CO2 into value-added products or alternative energy sources. Photo2Fuel project is working towards advancing CCU technologies using CO2 as feedstock and solar energy as power source to produce clean fuels and chemicals based on the concept of artificial photosynthesis. But what exactly is artificial photosynthesis? In nature, photosynthesis is the process by which plants convert sunlight, water and CO2 into oxygen and energy-rich molecules. Artificial photosynthesis is an emerging technology that, mimicking natural photosynthesis, captures CO2 and water molecules, efficiently converts them, and creates valuable organic molecules with the help of solar energy. In Photo2Fuel, artificial photosynthesis happens in biohybrid systems, an interesting new approach that brings together the powerful selective capabilities of microorganisms with efficient human-made light harvesting materials. At the heart of Photo2Fuel's biohybrid systems are two microorganisms, Mirella thermoacetica and Methanosarcina barkeri. Mirella thermoacetica is a bacteria known for its efficiency in converting CO2 into acetic acid, a key ingredient in many industrial processes under anaerobic conditions, which means in the absence of oxygen. Acetic acid is essential for producing plastics, textiles, and even food additives. On the other hand, Methanosarcina barkeri is an archaea that produces methane from CO2, also under anaerobic conditions. This methane can be used as an energy source, similar to fossil gas. But these microorganisms alone are not enough. To unlock their full potential, we need to harness the power of sunlight. This is where photosensitizers come into play.
The photosynthesizers which we are working on are of organic origin. So we use this specific hybrid system to put them on, as to say, on the microorganisms. The photosynthesizers are specific design that they can attach to our organisms and that they will harvest the light. So in a special way, the light will go to our photosynthesizers, and then the electron pathway will go on, and the electrons, our protons, will go further in our metabolism of the specific microorganism we use in the Photo2Fuel project.
Think of photosensitizers as the spark that ignites the whole process. Without them, the sunlight that powers the system couldn't be effectively used by the microorganisms. In the Photo2Fuel project, photosensitizers are carefully chosen to efficiently capture light, transfer the generated energy directly to the microorganisms, and stay closely connected with the bacteria, enabling CO2 utilization. In the Photo2Fuel project, we use organic photosensitizers that can be easily engineered to have specific light absorption properties and more environmentally friendly due to the absence of metals.
In our lab, we are culturing different archaea strains. For the Photo2Fuel project, we are focusing on the Methanosarcina barkeri. In our project, we try to add the specific photosynthesizers to the Methanosarcina barkeri and check whether they are producing under this specific conditions with sunlight and CO2, they produce methane. For this, we have to check, of course, the specific living parameters for the barkeri strain, and we have to check the culture medium for the parameters. We have to check the light intensity, light spectrum, for example, and of course we have to check whether they are producing methane or not. This we are doing mostly via the gas chromatograph. And we check, for example, the viability of the microorganisms via fluorescence microscopy.
As we continue our research, Photo2Fuel is preparing to scale up the most efficient system, ensuring we can move from the lab to real-world applications. This means refining separation technologies and conducting sustainability assessments, taking into account the environmental, the economic, and the social perspectives.
Renewable energies are really important nowadays and also in future. We want to reduce the CO2 and we want to get rid of or make substitutions of the fossil fuels, for example. So on the one hand, we use a lot of wind and solar energy, for example, which it's not so easy to store. On the other hand, we have a lot of CO2 production, which we also want to reduce. This in combination, and to have a look on the Photo2Fuel, we can combine this. We can use the sunlight, so the energy from the sun directly, and we can use the CO2 from different sources and combine them in our reactor and in the hybrid microorganism system to produce renewable methane, which can be used in every application as the fossil fuels, for example. Or in the other way, we can also produce acetic acid, which we can use as a renewable acetic acid to produce as a basic chemical.
As we look towards a future of clean energy and sustainable industries, projects like Photo2Fuel are valuable steps forward. By transforming CO2 from a problem into a resource, this project joins the collective scientific effort to address climate change. Together, these innovations are paving the way for a world where technology and care for our planet go hand in hand.
I just wanted to say thank you very much to our partner in the communication and dissemination, CINEA, for such an amazing video. Also to thank you very much, Maria Vieringer, a researcher from TCE, also a partner in the Photo2Fuel, working in specifically in the Work Package 2, for producing this amazing video that basically gives an overview of the project itself. Now approaching, as I mentioned at the beginning, the end of the approaching to its conclusion in the last 6 months. So thank you for waiting. We just recharge our batteries with strong coffee. And I just wanted to continue with the workshop over the next hour till finalizing it. And I just wanted to take the opportunity to present our next speaker, Morgan Ranier from the Noel Research Group as well. His background is chemistry. He's a chemist that gained experience through bioacademic and industrial placement. And from April 2023 onwards, he's been working as PhD candidate in the Noel Research Group. He's going to talk today to us about the electrosynthesis in continuous flow, specifying its challenges and opportunities. So Morgan, feel free to start. Thank you very much.
Thanks a lot, Alejandro, for the nice introduction. Can you hear me well in the chat as well? Okay, very nice.
Yes.
So as the introduction said, I'm going to be presenting today a bit about electrosynthesis in continuous flow. And it may sound like it's a black box into another one, but please bear with me, because in this specific case, the complexity is actually worth it. So going down to the definition of a chemical reaction, one can think of it as a distribution. One can think of a molecule as a distribution of electron densities. So the organic chemist is interested in changing these electron densities to create or break new bonds. And in this specific case of electrochemistry, we're able to reduce this bromomethyl cyclohexane to get this carbon-centered radical, which is going to be very interesting for downstream organic chemistry processes. And how can electrochemistry help to do this? You can look further into the electron transfer itself. There are roughly two ways you can achieve this one. Either in a homogeneous fashion, so on the top right, on the upper example, in the case of the cobalt complex. So this cobalt complex is able to reduce the ferrocenium ion because the highest occupied molecular orbital has an energy that's higher than the accepting orbital of the ferrocenium ion. But if you want to achieve a heterogeneous electron transfer, it's in a way much more modular, because you're going to do this through an electrode. And in this electrode, because it's a conductive material, you have electrons flowing, And by applying a potential to this electrode, you're going to modulate the energy of this electron. And by slowly increasing the energy of this electron, you're going to be able to be higher in energy than the accepting orbital of the ferrocenium ion, and therefore transfer the electron to achieve the reduction. And so that's the way electrochemistry works, basically, modulating the energy of electrons. And beyond organic chemistry examples, and some examples that will be actually quite relevant to this consortium of working towards a climate neutral EU, you already have examples in the lab, but also in the industrial scale of valorization, electrochemical valorization of lignin and to transform it into renewable feedstocks, or the direct CO2 reduction to change this greenhouse gas into added value small molecules. So if we go back to the practical aspect of electrochemistry, and if we actually even go back to the first ever reported electrolysis experiment reported by Michael Faraday in the 1800s, he must have used a setup that looked like something that you can see here on the screen. A working electrode, a counter electrode to close the electric circuit, and a connection to a power supply. Now, the main limitation you can see here is because electrochemistry is a heterogeneous electron transfer, the diffusion of molecules from the bulk to the electrode surface will be crucial. One order of magnitude you need to keep in mind is that a molecule with an average diffusion coefficient will travel 50 micrometers in a second, but 1.3 centimeters in a day. And this is how we justify looking into microfluidics. Because with microfluidics, the electrolyte is now flowing between the anode and the cathode, like in a sandwich, with a micrometer scale gap. And thanks to this micrometer scale gap, you get a lot of benefits because all of a sudden the diffusion of molecules is not limiting anymore. So you have a much better mass transfer. You also have a much more scalable production by using many reactors either in parallel or in series by just letting them run over time. And also you have an inherently safer production because of microfluidics. You will have a heat dissipation that will be enhanced, so hotspots will be removed. And in case the reaction gets out of control, you can unplug your reactor, and therefore, because you have a very small active surface, the reaction cannot go out of control. And because you have such a limited space between the anode and the cathode, the resistance of the solution is not that critical anymore, which means that you can remove the supporting electrolyte of your solution. Then the question we are interested in this group, in the Noel research group, is why then is there such a gap when we think of electrosynthesis, so electrochemistry for organic chemistry, and the combination with flow chemistry, because it seems that there are a lot of inherent advantages. So what's going on there? What's even more interesting is that in theory, you can tailor the design of your reactor to the reactivity you want to achieve. And here are 4 examples that highlight this. On the top left, as an example, you have a filter press type of reactor. So 2 parallel electrodes that enable this annihilation reaction in the combination of gases to get this isoquinolines. On the top right, you have these rotating electrode reactors that can enable to handle slurries so that there is no clogging of the system to transform cortisone into adrenosterone. On the bottom left, you can combine light and electrochemistry as activation methods to enable photoelectrochemical activations. And here in this case, the light will generate the chlorine dots that will enable the hydrogen atom transfer, and the electrochemistry will take it from there to further oxidize and enable the substitution. And lastly, you can even use gases in electrochemical flow reactors by using gas diffusion electrodes that maximize the contact of the gas with the solution and therefore enable the electrolysis, here in the case of conversion of nitrogen to ammonia. So added to the previous advantages that we saw, you can add the tailored reactor design to fit exactly the needs of your chemistry, and also the ability to handle multiphasic mixtures. And this is really what we're trying to make the most out of in the NOEL research group by having our own reactor design built in-house. And the most interesting elements you need to keep in mind here are the working electrode, the counter electrode, and the PTFE gasket between the two. So you can change the thickness of this PTFE gasket to change the distance between the electrodes, and this is where the electrolyte is going to flow. So you have a great reactor design added to a nice electrochemical team. You can think that indeed discovery is on the way. And so what we focused on is reactions of cyclopropanations very recently. What we wanted is enable these cyclopropanation reactions from feedstock chemicals, because cyclopropanes are interesting in organic chemistry and bioactive molecules at large. So using feedstock chemicals like geminal dichloroalkanes, such as dichloromethane, the solvent, we can activate this compound to generate the corresponding cyclopropane. And that's how we develop this nickel-catalyzed electrochemical continuous flow cyclopropanation. You can see here at the bottom how general the method is, tolerating a range of complex double bonds. But what we were mostly thrilled by, and this is really where the impact of flow can be seen, is that we could enhance the throughput of this reaction by a factor 20, getting therefore just by having 5 reactors in series, and then we're able to get above 2 grams of the desired cyclopropane in less than 7 hours at the laboratory scale. So as a conclusion of this presentation, to give a last few words, so the reason why flow electrochemistry is not implemented more, in our opinion, is not because it's lacking benefits or it's because it's too complex, but just because people have limited exposure to flow technology at large, which makes them see it as a black box, like we said earlier. So people get limited training and they are more familiar with the batch setups that have been around since the 1800s with Michael Faraday. But it's time to change this. So this is our aim in the NOAA research group. And also, one of the limitations of flow for now is that it's quite difficult to change the electrode materials. But I'm sure some things will come along. We're working on this. And for the last infographic that I would like to show you about the importance of electrochemistry in flow, or electrochemistry at large, is this recent OPRD that came out a few days ago that does a survey of 15 pharmaceutical companies. And in orange, you can see in what type of projects they are using electrochemistry at the moment. And in blue, you can see where they will be using this technology in 5 years. And you can see that now at the moment, it's mainly discovery, so route exploration. But what you can see is that in 5 years, they actually are planning to double their capacity in almost all fields. And especially, I draw your attention to the bottom of this infographic showing that in 5 years, they almost all want to have commercial manufacturing processes thanks to electrochemistry. And this is where flow electrochemistry will be crucial. On this note, I can just thank you all for your attention and thank you for the consortium for inviting me today. And I can also thank the rest of the group, without which all of this would not exist. Thank you very much.
Thank you very much, Morgan, for such a nice presentation. Indeed, we are facing with many technologies that are being emerging, that are being discovering, that we are being working towards escalating and promoting. And definitely it's good to know that over the last slide that you have shown that for the piece of research in which you are working specifically, it seems like something that is going to happen definitely in the future. I just wanted to highlight that the opportunity of you participating in this workshop, we are going to do our best efforts as well to communicate, to disseminate the outcomes of this presentation. We can see this as a good opportunity necessary to enhance that promotion. So definitely, I just wanted to say thank you again for the presentation, for being very concise and clear in a very complex topic for some of us. But yeah, I hope this works perfectly, and makes a better outcome of your research. So I don't know if there is any other question. I think, yes, from Matteo. Do you need, is this question, Matteo, about the topic, right? So do you need a carbonyl for the reaction, and in particular an ester, or can you also use a different EWG? So do you want me to repeat?
So I guess you're talking about the cyclopropionation reaction? Yeah. So yeah, that's a good question, and one we were surprised by, because we do need an activating group that can be either an electron withdrawing group, but also just an aromatic motif is enough. So we do need this activating moiety, but actually you can also have a para group on this aromatic moiety that is electron donating, like an aniline with a styrene motif, and then the reaction will still work and even tolerates like the free NH. So that's interesting. And so that's why in the paper we were not sure about the nature of the philicity of the carbene we have, and we think it could go through a radical type of pathway. That's why we do need this activating motif, but it can be aromatic rich, poor, or electron withdrawing. Yeah. Thanks.
Thank you, Morgan, for the clarification on this question. We're just on the time for passing to the next presenter. There is Lars van der Zee. Just to make a brief presentation of our next speaker. He's a PhD candidate in physical organic chemistry by the University of Amsterdam, working under the supervision of Professor Chris Slutweg. Lars investigates the use of both thermal and photo-induced single electron transferring frustrated Lewis pair and main group chemistry for the formation of radical ion pairs, with the goal of activating small molecules like methane. And during the workshop, he will be presenting an overview on the design principles of the donor-acceptor systems studied in his research. So, Lars, the floor is yours. Thank you very much for your presentation in advance.
Yeah, thank you for the introduction. So yeah, I will be talking about donor-acceptor pairs, specifically in the field of frustrated Lewis pairs. So let's start off with what are Lewis acids and bases. Just some basics. The Lewis acids are compounds with a vacant orbital that is low in energy and can accept electrons. Examples are, for example, boron or alumina compounds. While on the other hand, Lewis bases have an electron pair high in energy. These examples are amines, phosphines. There are many of these. And if you combine these two, you form a complex, what's known as a classical Lewis adduct. Here, a covalent bond is formed between the Lewis acid and base by sharing the lone pair from the Lewis base with the Lewis acid. And at the bottom left, you see some examples. For example, ammonia borane, but also the commercially available form of 3-fluoroborane as the ethyl ether complex. But also, already in the 50s, there are examples shown of combinations that are not forming such a classical Lewis adduct. And this we can see as the starting point of frustrated Lewis pair chemistry, where bulky side groups of the Lewis acid and base prevent the formation of Lewis adducts. Frustrated Lewis pairs have over the years shown a lot of reactivity towards various substrates. I showed here a couple. Hydrogen is a very prominent one, but also CO2 is very well known for binding FLPs and has also over the recent years been functionalized further towards methanol, methane, and a lot more. How do FLPs work? Well, they first form a so-called encounter complex where the Lewis acid and base are coordinated towards each other. Subsequently, a substrate enters the reaction pocket and gets activated by cooperative donation and accepting of electron density to form the final product. And in this way, as I said, a lot of substrates can be activated, but we're in search of a higher reactivity, more reactivity. For example, apolar bonds such as CH bonds from, for example, methane cannot be activated in this heterolytic 2-electron way. And therefore, we are looking for something else. And this is in the form of radicals, specifically radical ion pairs. And radicals have been discovered already quite a few years back in the field of first-state Lewis pairs. For example, in this combination of amine with this borane, and that gave, upon just stirring over 3 days, the radical cation. But later on, also in the more classical FLP of this phosphine and borane, also the radical ion pair has been discovered, although initially first and only the radical cation has been found. But our question was, how are they actually formed? Because if you do the calculations, you see that by calculating the ionization energy of the phosphine and electron affinity of the borane, so basically how easy the phosphine loses an electron and the borane accepts an electron, you find an energy gap of 2.4 electron volts. This is over 50 kcal per mole. So according to the Boltzmann distribution, the equilibrium will be completely on the closed shell state and there will be no radical ion pair formed at all. But 2.4 electron volts is also about 500 nanometers. So that is in the visible light. So if you look then carefully at the UV vis spectra and you compare the UV vis spectra of the individual components in red and blue and compare them to the combination, you see an additional absorption band at 534 nanometers, and this is what we call the charge transfer band. If you irradiate this band, you will form the radical ion pair, which we were the first one to detect with EPR spectroscopy, both the radical cation, the blue trace, and the radical anion, the red trace. And we could also further characterize the radical ion pair using, for example, transient absorption spectroscopy. So this is all very nice photo-inducing electron transfer, but what happens if we go to a way stronger electron acceptor, for example, the 3-2 cation? You see suddenly the energy gap decreased to only 0.29 electron volts, and this gives us the opportunity to already form the radical ion pair at room temperature. So even at room temperature, we could detect both the radical anion and cation in solution. We brought this further and studied it more, and for this we switched to quinons as electron acceptors. There were already some examples of the radical ion pairs reported in literature, and also we have found some. For example, this example where we form an radical ion pair in situ that yields some CH activation upon formation. But we further studied with the combination of 3 aryl amines and DDQ, and really focused on what happens with the system upon tuning the electron donating capabilities of the amine. For example, when taking the para-bromo, we saw no charge transfer at all at room temperature, while when we tuned the system to a more donating group, we could find some the formation of the radical ion pair, both in solution and in the solid state. So to conclude, we're working with radical ion pairs that you can form both photo-induced, which are characterized with a new UV vis absorption band, but also a thermal single electron transfer where the redox potentials are more in equilibrium. And this is a way to go to the activation of small molecules. So in the end, let me thank the group and all of you for your kind attention. Thank you.
Thank you so much, Lars, for such a Nice presentation, also very interesting. Just a quick question on the actual, maybe I didn't get that, or like I can see that this is a very basic science, the research, fundamental science that you are investigating in the group. Is there, what's the actual sector or point towards you can apply this research that you are investigating, which what's the actual advantages of the discoveries that you are carrying out in your investigation?
Thank you for the question. It's indeed really a fundamental study right now, but we're really hoping to apply it for deep CH activation, as their radicals really need to be used. You cannot do it with two-electron chemistry. So hopefully, in the end, at some point, we can, for example, activate methane, split the CH bond.
Thank you so much for the clarifications. Indeed, it's quite promising. It's quite fundamental, but it has a lot of promising future, as you have explained. I just wanted to not delay on the time scale. We are really going really well on the timetable for this, but I just wanted to go on to our last presenter to finalize the round of speakers for the workshop to date. And just we don't have any other questions for last, so I just wanted to introduce Matteo Damian, a PhD candidate in biocatalysis at the University of Amsterdam as well. Matteo is a synthetic chemist driven by the remarkable potential of nature's enzymes to transform chemical synthesis. His PhD research is focused on pioneering green and sustainable methodologies for producing high value molecules, including pharmaceuticals as well. With a deep curiosity for enzyme reactivity, Matteo has revealed innovative applications for enzymes often considered traditional, pushing their catalytic capabilities beyond those found in nature. During the workshop, he will be presenting how the catalytic promiscuity of these enzymes can redefine the synthesis of challenging but crucial chemical building blocks, such as acyl derivatives, towards more efficient and sustainable chemical processes. So thank you very much, Matteo, in advance for your presentation. The floor is yours. So feel free to start with your presentation. Thank you.
Hello and welcome everybody. I'm Matteo, and I'm a PhD candidate in the BioCat group of the UVA. And today I'm gonna show you a case study from our group, a new-to-nature activity of alcohol dehydrogenases, that are enzymes that have been known for more than 100 years, and we try to revolutionize their use in organic synthesis. First, I want to show you what my group is actually doing. So we start from enzyme engineering. We do a lot of cascade reaction. We focus on in vivo biocatalytic cascade. We also study the degradation of polymers through the use of enzymes. Lately, we are also focusing on biophotocatalysis and bioelectrocatalysis. So biocatalysis merged together with photocatalysis and electrocatalysis. And then also we try to discover new reactivity of enzymes. Related to this topic, in the past years, the group has published already something. And here I picked three papers from the last 5 years. And from these, we're gonna dive into my topic. That is gonna start with a general introduction about alcohol dehydrogenases. First, we are gonna produce the enzyme altogether. So we start with the E. coli cells that we are using. We incubate our plasmid. In the plasmid, there is the information to produce our enzyme, and then we start the cultivation on agar plate. Then we overexpress the enzyme, and then eventually we will purify the enzyme to get the pure product and the pure enzyme, and use it for our synthesis or our transformation. Alcohol dehydrogenases are enzymes that, as I said, have been known since the 19th century, and they are commonly used for the catalytic equilibrium between the carbonyl compound and their corresponding alcohol, both ketones and aldehydes. They are mainly used for the reduction of prochiral ketones using the cofactor that can be NADH or NADPH, leading to one of the two enantiomers selectively. That's why they are so important, thanks to their selectivity. We can also study the selectivity of the enzyme. If we look into the active site of the enzyme, we can see that the cofactor is pointing one of the two faces of the carbonyl compound, and depending on the face that is facing to the hydride, then we can achieve the R or the S product. This is in general the normal reactivity of alcohol dehydrogenases, and again, depending on the phase, we can get R and S. But in the 50s already, researchers have shown some side reactivities of this enzyme. In particular, starting from methanol, they were able to achieve the formation of formic acid with the horse liver alcohol dehydrogenases. More than 20 years later, in the 70s, they were able to produce a lactone starting from diols, again with the same enzyme that I mentioned before. And more than 40 years later, in the 2018, the same enzyme was able to catalyze the formation of lactams starting from amino alcohols. If we study the mechanism of this reaction, then we can see how the alcohol dehydrogenases is catalyzing the oxidation of the alcohol to the corresponding aldehyde using the normal reactivity of this enzyme. But then the nucleophilic attack leads to this hemiaminal or hemiacetal intermediate that we see here that can be oxidized further to the corresponding lactone or lactam in this case. So my question was, is it possible to use the side reactivity of alcohol dehydrogenases for the synthesis of acyl derivatives? In particular, I wanted to move from the typical synthesis and typical use of alcohol dehydrogenases that are used for the enantioselective reduction of prochiral ketones to the synthesis of these acyl derivatives, oxidizing this particular intermediate. Therefore, I tested the reaction in a particular condition. We were able to achieve the overoxidation of the primary alcohols to the carboxylic acid. But then we tested with different nucleophiles. So, for example, adding amines to the reaction media, we could achieve the formation of amides. Then we tested also with thiols. So the combination of alcohols and thiols was leading to the formation of thioesters. And finally, we were also able to selectively oxidize one alcohol to make it coupling with a secondary alcohol and get the formation of the ester. These are novel results, and this novel reactivity was very promising to us. Therefore, we decided to go on and perform a first round of enzyme engineering. So basically, we studied the active site of the enzyme. Studying the active site of the enzyme, we recognized some residues that could interfere with the reactivity of the enzyme. And we wanted to expand the substrate scope, especially of amides and thioesters that are crucial molecules, but very hard to make it in an efficient way. Through the first round of enzyme engineering, we were able to move from a limited substrate scope regarding the amine site of the amides, in which it was possible to achieve only primary and methyl-amides, to longer chain amides such as ethylamide, propylamide, and so on. And we are still screening other substrates because the results are very nice. And we did the same with the thioester. Again, we had a limited substrate scope at the beginning with the wild type enzyme, but after the engineered, we were able to achieve better results and the broader substrate scope. So in conclusion, I want to leave you with this message that pushing enzymes towards a condition that are not natural conditions can lead to novel reactivities. We created these new synthetic pathways for the synthesis of acyl derivatives, and these pathways very robust and it has a large applicability because actually we were able to synthesize more than, here I wrote 100, but actually there are 500 molecules that we obtain in this way. And thanks to the enzyme engineering performed by a colleague, we were able to broaden the substrate scope to achieve better results. So I want to thank the coordinator and the participants and the partners and you all for their attention. Thank you.
Thank you very much, Matteo, for such a nice presentation as well on the promiscuity of the alcohol dehydrogenase. Actually, I have just one follow-up question on regards of the actual variability and adaptability that the enzyme has. So it's something that so the metabolic engineering that you have to do is more about like you just drop the enzyme in your cultivation media or in your actual experiment media, and you just leave it there perform, or is this something that requires very specific conditions for making the reactions for each of the specific products that you want to obtain?
Thank you, Alejandro, for your question. So I didn't want to give too many details since it's unpublished results yet, but actually we just pushed a lot the condition. So there's a very harsh condition in which the enzymes are not naturally found. And in this condition, we found this the possibility to realize these transformations. Obviously, the conditions are very harsh. Then, therefore, the enzyme is not going to survive forever. So the reaction are quite fast, considering biocatalysis. And afterwards, the enzyme is completely degraded. So now, what we are also focusing is the mobilization of the enzyme to make it more stable and to make the approach more sustainable and let's say for a longer to reuse the enzyme more times.
Perfect. Thank you very much for the clarification. I just I was trying to add some you know, more following up on conversation on that. It's more a background for that I'm more related to, and it's quite interesting what you have shown, and I just wanted to get more clarification on the actual part of the experiment. So thank you so much for that. With this, this is the end of the presentations. I can see that we don't have any additional questions. Do you have a question, Morgan? So can you ask over the microphone? Yes, thank you.
Yeah, thanks, Matteo, for the nice presentation. I liked it a lot. I'm very not familiar with biocatalysis, so my question would be about like cost comparison, because unfortunately that's what like drives most of the research and everything. What would be the comparison in terms of the cost of a transition metal to make the structures you're making and the cost of a biocatalyst in terms of like milligrams, like euros per milligrams? Do you have a number? Thank you.
So thanks for the question, very interesting, and luckily I can give you an answer because I was trying to understand how green and sustainable was my method compared to the industry one. Let's say I can give you a number about the production of the enzyme. In general, we're using a cell-free extract enzyme. That means that after the production of the cells containing the enzyme, the overexpressed enzyme, then we just slice them with a sonication, and then we lyophilize them. For the production of 10 milligrams of this enzyme, we calculated an energy required that is around 20 kilojoule. So I cannot give you directly a cost of this kilojoule. I think it depends, but yeah. But this is the comparison. And also, if we compare, for example, the amidation step compared to the one that is present in literature, if we compare this work to the pioneering work from Milstein in 2005, in which he was coupling alcohols to amines to get amides, the conditions are completely different because he was pushing the reaction at reflux in the toluene, that means 120 degrees overnight, and we were able to achieve basically the same results, but in 3 hours and at room temperature at 25 degrees. Obviously, the scalability is also depending on the substrate loading. And in our case, the substrate loading is still lower compared to the one reported by Mills, but I think it's something that we can improve later on, or it can be improved, let's say.
Nice.
Thank you so much, Morgan, for your question, and Matteo for the clarification. Also, I'm sorry because I missed a previous question from Lars' presentation. If you don't mind, and just finalizing with Matteo, I wanted to get back to that actual question from Morgan to Lars, if you don't mind, just for everybody to, and because we have some extra time just before finalizing the whole session. I just wanted to come back to Lars and ask this question. So Morgan asked Lars, what is the difference in terms of applications of the FLPs and the radical FLPs? If you can contribute and clarify on that, it will be much appreciated. Thank you.
Thank you for the question. Regarding the classical FLPs, what you see is typically you need one side of the substrates needs to be a bit more positive and the other side negative. So you need some polarization in there. Carbonyls are really great for activating with FLPs. And these FLPs have been around now for about 2 decades, so it's a wide substrate scope. Regarding the radical counterparts, the radical ion pairs, these have been discovered only a couple of years ago. So there's not much known yet, but there is a recent paper which used the formation of a radical ion pair and really could activate CH bonds. So you can then way less polar bonds you can also activate. So there's the strength of the radical ion pair should come in. I hope that answers your question.
Yeah. Thank you.
So this general question about biocatalysis, Morgan, is the one that you have already asked, right, to Matteo? Okay, thank you very much. So that's already being responded. So if there is no extra or any other question to our last presenters, I would really like to take the opportunity to conclude the session. I would really like to take the opportunity to thank you all for being here today. It's been an amazing opportunity to know such very promising researchers in the field of organic chemistry. Thank you very much for sharing your pieces of research today. And I hope you have the best of lucks to advance on that, and hopefully to have very promising and enriching publications in science. I just wanted to also conclude by giving thanks so much to CINEA for organizing and helping on organizing this workshop, also to Romina and Webinar Helden, who are the main providers of the technical aspects of carrying out this session today. Everything were really smooth, very fine, and we are very happy to come out with such a nice outcome out of the consortium meeting of the Photo2Fuel. And also, just finalizing, thank you very much to the University of Amsterdam, to Noel Research Groups for being such a nice host over these 2 days that we are spending here for the Photo2Fuel consortium meeting in Amsterdam. And this is all. We will be recording and sharing, trying to disseminate the outcomes of this session over our social networks and also the Photo2Fuel website. So hopefully this will also reach out to more as many people as possible and help us on our research outcomes. So from my side, that's all. Thank you so much again for your contributions, and hopefully we see you soon in the future. Thank you very much. Bye.